So I would like to welcome you all to the first InterCat seminar, and I'm very happy today to introduce our speaker, Professor Alec Wodtke. So Alec got his PhD from Berkeley University under supervision of Whitey Lee, and he moved on to do a postdoc at Göttingen University under Peter Andresen, before he returned then to take up a chair as professor at UC Santa Barbara. In 2010, he went back again to Göttingen to take up a chair as professor at Göttingen University and as Max Planck director, heading the Surface Dynamics department at the Max Planck Institute for Biophysical Chemistry. So Alec has left a trail of science and nature papers in his wake as a testament to his ability to always push the limits of what is possible in experimental surface science. And today he will tell us about the first demonstration of the use of a superconducting nanowire single photon detector in a surface science experiment. So please, Alec, the screen is yours.
Okay, thank you very much for this nice introduction. Can you see my presentation?
Yes.
And you can hear me okay?
Yes.
Okay, good. First of all, thank you for the invitation to speak to you. I learned about your International Catalysis Center for Interstellar Phenomena, and it sounds very interesting. And I don't know very much about that field, but Liv thought that the work we're doing with infrared spectroscopy may be of interest to you. And so I think we have an opportunity to maybe exchange some ideas and knowledge, and perhaps enrich both our scientific lives. So you know already the title, so I'll just go on to the outline of the talk. It's about infrared spectroscopy and new technologies for doing that, and so part of my talk will be about infrared light detection with superconducting based light detectors. We've used that to carry out laser-induced fluorescence experiments in the mid-infrared on molecules adsorbed to surfaces. An experiment that I always considered in my early days as physical chemistry as kind of hopeless. Any laser-induced fluorescence with infrared light seemed like a bad idea, but now it's no longer a bad idea. We looked at a very simple system of molecules, carbon monoxide molecules on a sodium chloride salt crystal, and there you can observe the vibrational energy pooling phenomenon in great detail, and I'll show you about how we've been able to find out how that works. It's a way to make samples with very large vibrational excitations. And it turns out there's a prospect to use this even to drive some reactions through control of vibrational energy, and even to create kind of light harvesting systems where you can have a strong absorbing chromophore which produces a large number of vibrational quanta, and then through careful design of a model system, we've shown that you can condense a large fraction of those vibrational quanta into a very small volume, and use that also to drive a reaction. Okay, so maybe I don't need to do this in this audience, but I want to just show a slide about infrared spectroscopy. Spectroscopy, of course, is an extremely useful tool, but you should always ask, what kind of spectroscopy do I want to do? And my answer to that is very simple, and that is, if possible, always do infrared spectroscopy. And the reason for that, especially if you're working with molecules on surfaces, is that it's not only, it's a very information-rich form of spectroscopy, but for several reasons. One reason is that the relaxation of the excited states is relatively slow, so typically taking place on picosecond timescale, which means you still can have lines which are on the order of a wave number or even narrower. And so you can just establish line positions very, very accurately. If you compare that, for example, to electronic spectroscopy of molecules on surfaces, relaxation times are femtoseconds, And so you never have a great deal of precision in determining the positional lines or resolving multiple lines from one another. Another big advantage is that infrared spectroscopy almost always means you're working on the ground electronic state of the system. So if you should like to collaborate with theoreticians to understand your spectra, density functional theory is a very useful tool. Whereas if you're working on excited electronic states, you probably have problems to get good theoretical information. For my chemist friends who are not spectroscopists, I like to describe infrared spectroscopy as very similar to nuclear magnetic resonance, in the sense that your line positions are extremely sensitive to the environment in which the molecule finds itself. So a CO molecule that sits at a step site or a terrace site will have a different infrared absorption frequency. Whether it has neighbors, other CO molecules nearby will change its frequency, so it can be coverage dependent. And even if you form an ordered structure and different orderings of the structure are possible, then the line positions can change, and even doublet features can appear. So quite stark changes in the spectroscopy. So now that I've convinced you that IR spectroscopy is really what you want to do, we can ask the question, what's the best way to carry out infrared spectroscopy? And this brings us to a very general conceptualization of how to do measurements for detecting molecular absorption of light. And there are basically two different ways. One is a technique we call a flop out technique, which is just Lambert-Beer's law type infrared absorption spectroscopy. And in that kind of experiment, what you do is, I'm going to turn on my laser pointer here, I guess. What you do is you have a light source which fluctuates up and down, and you come to a transition, and you can see a depletion of the signal. Here is shown an enormous depletion of 30% of the depletion, of course easily detected, but you can just immediately see that detecting 1% depletion will be much smaller, and detecting parts per million depletion will be even much smaller. And so this kind of spectroscopy is obviously sort of guaranteed to be a relatively low sensitivity kind of spectroscopy. It's also what we almost always do in the infrared. It's much preferable to do what's called a flop-in spectroscopy, where you have some kind of a background and you tune your light source, and when you come on a resonance, you have an enhancement of the signal. And then, although this picture maybe does not look better, if you're clever, you can usually find ways to make this background smaller and smaller and smaller. And as a consequence, you're measuring a finite signal on top of, if all goes well, no background whatsoever. And then you basically have Poisson statistics determining your noise. The square root of the number of photons that you detect is your noise, and you're able to increase your signal to noise just by averaging over longer and longer times. This is all equivalent to what I like to call the Peter Andresen rule. My postdoctoral advisor, Peter Andresen, had a very simple rule about how to predict if an experiment would be successful or not. And he said, any experiment that produces OH, ultraviolet fluorescence, is guaranteed to work. And to understand what's behind that, again, it's a flop-in type of spectroscopy. If you do OH-LIF, you take a laser and excite it at one wavelength, put in some filters to block this wavelength, and you can see fluorescence at another wavelength. You can also use timing, because the fluorescence lifetime of the excited state is a microsecond, so you can just fire a nanosecond pulse of light, excite the molecules, and watch the microsecond time decay. So it's pretty easy to set up an experiment where you have strong signals and no background, and it's the ideal case of this flop-in spectroscopy. The reason that OH laser-induced fluorescence works is because we have the photomultiplier. The photomultiplier has enabled laser-induced fluorescence, and if we could use this in the mid-infrared, we would. It's a 200 euro device that when a photon hits a photocathode, electrons are emitted, and we drag those electrons to a multiplication avalanche dynode chain. And from a single photon, we can typically get 10 to the 6th to 10 to the 7th electrons, which we can, within a few nanoseconds, or even less than a nanosecond in a good photomultiplier. And that's something that you can easily see on an oscilloscope or many other recording devices. Of course, the reason that we can't use these in the infrared is that these depend on the work function of some photocathode material, and even with the most favorable photocathode material at wavelengths longer than about 850 nanometers, you're really just out of luck with photomultipliers. So in the infrared, we have to use different tricks. And so detecting infrared photons has almost always involved using semiconductor devices that are based on concepts that are easily understood through the electronic structure of silicon. And here you can see silicon where it is in the periodic table in the group 4. And it's a semiconductor, which means it has a band gap, so it has a valence band, and it has a conduction band. And this band gap is about 1 electron volt, so if a 1 micron photon comes in, you can excite an electron from the valence band to the conduction band, and you can record a current in the conduction band as a result of the excitation of the photon. So it's a bit like the photomultiplier in that you have kind of a photoelectric effect, but the electron doesn't escape the material, it's just into the conduction band where you can then collect the electron and read it out. You can actually do much better than silicon if you want to go into the mid-infrared, and instead of just using group 4 materials, you take some group 3 and some group 5 materials, or some group 2 and some group 6 materials, and you can make materials like indium antimonide, which is possibly the most popular material for infrared detection. Again, basically working in the same way as I just described, but now the band gap in indium antimonide is about 1/4 of an electron volt. So you can now do experiments out to longer wavelengths than 5 microns. Mercury cadmium telluride is another very popular material, about 1/2 an electron volt band gap that's working out to about 2.5 microns. This all sounds like great news, and we should be overjoyed, and why don't we use these detectors? The problem is that these detectors have internal dark current, and so it's not enough to just detect a photon through this internal photoelectric effect. We have to actually figure out how many photons are needed to be equivalent, to give an equivalent current to what our dark current in the detector is. And so we have to understand the concept of the noise equivalent power. And all this is the power of the light that you need to come in, which will then be equivalent to your dark current in your detector. And a typical number for a liquid nitrogen cooled indium antimonide detector, you cool them because this dark current is due to thermal excitations of the electrons from the valence band or the conduction band. A liquid nitrogen cooled indium antimonide detector typically has a noise equivalent power of about 10⁻12 watts per root hertz. And if you do a little calculation about how many photons that is at 5 microns, you need to get 10⁻12 watts per root hertz. You need to have about 25 million photons per second coming in. This is really a kind of a roundabout rule of thumb about what the detection limit of these indium antimonide detectors is. And if you compare this to a photomultiplier, which can actually detect single photons with 30 or 40% efficiency, you're obviously really quite far away from where you'd like to be. So just to sum this all up, if you want to work with photomultipliers, you have a fundamental wavelength cutoff related to the work function. If you want to work with semiconductors in the infrared, you have a fundamental cutoff due to the band gap. In addition, you have this problem that the electron, is being measured on a background of thermal noise, essentially. And in addition to this, these semiconductor devices turn out to have really bad time resolution. So if you want to do some pump probe experiment or time resolved experiment, it's actually quite difficult. So I want to talk to you about a new kind of tech. Well, it's actually not that new anymore, but it's matured to the level where it's really useful for people who are not specialists in this field. And these are materials that are based on superconductivity and detectors that are based on superconductivity. And we got into this through a collaboration with an excellent group in Boulder, Colorado at the National Institutes of Standards and Technology called the Faint Photonics Group, led by Sewu Nam and his colleagues Varun Verma and Rich Mirren, and they've been extremely helpful in helping us get into this field, which I'm really grateful for. So let me tell you about what they're working on a variety of different superconducting technologies. Let me tell you about the one that I think is the most interesting for physical chemistry and chemical physics and molecular science, and that's the superconducting nanowire single photon detector, which we call the SNSPD. And these were actually developed first in Russia in 2001 using a superconducting material, niobium nitride, which is a crystalline material and is superconducting at a temperature that's not so low so that you can still just use a simple liquid helium-4 refrigerator to get this detector to superconduct. And so I just explained to you the basic principle of this thing. Here's a picture of a superconducting nanowire detector, and if you zoom in, what you see is a meandering nanowire going back and forth over a region of space to map out an area, so that you actually have a finite-sized detector. And here's an example. You can see these are still quite small, where it's 10 microns by 10 microns in size. The nanowire is 40 nanometers thick. In other words, its height away from the substrate, and they're anywhere from 30 to 80 nanometers wide. And if you look at how long this nanowire is as a single nano object, it's almost a millimeter long, okay? So fabricating these things turns out to be the key technical challenge to make them really quite useful, because you can imagine making this very long, skinny, crystalline material over nearly a millimeter in length. And actually, you'd like to have it a lot longer, because you'd like to have this thing be a millimeter by a millimeter square detector. But you want to make this thing somehow with no defects in it is not going to be so easy. And particularly for a crystalline material where you just have crystal grain boundaries periodically, this can be actually quite challenging. Nevertheless, these were the first ones that were developed, and they work quite well. And I can show you in principle how these things work. You have your nanowire, and you put a bias current through it. So you have superconducting current going through of a few microamps typically. And initially then the resistance is 0, and you measure no voltage across the wire. And at some point a photon can come and be absorbed by the niobium nitride material. And this thermal energy from the photon will create a local hotspot where the superconductivity now breaks down. And because the nanowire is so thin, the residual superconducting current now has to pass around this hotspot. And in this region of narrowed superconductivity, you now go over the critical current density for superconductivity, where it also breaks down in this region all the way to the edge of the nanowire. And then the superconductivity breaks down across the entire nanowire kind of in a catastrophic way. And you get finite resistance, and you get a voltage response in this, can be as big as a couple hundred millivolts. And that you can easily detect with ordinary electronics. Then the heat is dissipated into the substrate, into the sapphire substrate. It cools back down, and it goes back to its superconducting state, and you're ready to record a new photon. So this is a single photon detector. This, of course, can be used at any wavelength, and there's no fundamental cutoff, but it does depend strongly on the wavelength. And in this plot, what I'm showing here is the dependence on this bias current that you put onto the detector. So if this is called the switching current, if I go to a current that's too high, it will switch to the non-superconducting state. But if I have a bias current that's a fraction of this switching current, then I can detect photons. And so if you imagine here like a 500 nanometer photon, and I have the bias current at, say, half of the switching current, then you can see I've already saturated the detector. I'm detecting, it turns out, nearly every photon that is absorbed by the nanowire. I get a pulse. And if I go to higher switching currents, then I don't have any improvement. if I leave it here, say at about 50%, and I start lowering the energy of the photon by going to longer and longer wavelengths, you see that the probability that the hotspot that I create produces a complete catastrophic breakdown of the superconductivity is reduced. And so I become less sensitive to longer wavelength light. Then what I have to do is increase the bias current to come closer to the switching current, and then low energy photons can more easily lead to this breakdown of the superconductivity. I can detect longer and longer wavelength lights. What I want you to notice here is it depends on the width of the nanowires. These niobium nitride nanowires were fabricated at 85 nanometers width, and to go to even longer wavelengths, one needs to make these nanowires even much narrower. And so nanowires have been made so-called ultra narrow niobium nitride nanowires, only 30 nanometers in width. And now you can see the 2 micron light is nearly saturating at about 60% of the switching current. And if I now play the same kind of games, I can efficiently see light out to about 5 microns with quite good detection efficiency. But also take notice, for these ultra narrow nanowires, now the detector has become 1 micron by 1 micron in size. So it's even more subject to fabrication problems. And so the detector has to be made smaller and smaller in size as well, which can be a big disadvantage, because if you're working with a fluorescing sample, it's fundamentally a millimeter in size, because you're, say, exciting it with a laser beam a millimeter in size, then you'd like to have your detector also be a millimeter in size so you can collect as many photons as possible. So this niobium nitride is no longer the material that I believe people should be using. The group in Boulder has established essentially the same kind of detectors with the same kind of physics, but they now use a material called amorphous tungsten silicide. And there are a couple of advantages of this material. The main one is that amorphous tungsten silicide is not crystalline; it's a glass. It's an alloy of tungsten and silicon, which is literally a glass. And a glass has many interesting properties, one of which essentially cannot have any defects. So you can make these nanowires much more easily without worrying. There's never going to be any crystal grain boundaries, for example. So the other thing is that's very interesting about this material is it actually has different superconductivity properties, and so the superconducting splitting is more favorable in such a way that if I have a photon of the same energy on niobium nitride, it might make a very small hotspot. On amorphous tungsten silicate, it makes a much larger hotspot. So this just means you can fabricate your nanowires with much wider nanowires. Instead of having to work with 30 nanometer nanowires, now you can work with 100 nanometer or 150 nanometer nanowires, and you still get good response. So we're working now with these amorphous tungsten silicide nanowires, and I'm going to tell you all the stuff I show you will be based on that. And here's just an example of the use of a 5 micron infrared photon detected with one of these amorphous tungsten silicide SNSPDs. And what you can see here is that you get a strong breakdown of the superconductivity, a 30 millivolt pulse. It recovers in about 20 nanoseconds. The rise time is sub nanoseconds, so you can really use these for very precise timing. One disadvantage is the amorphous tungsten silicide needs to be operate at very low temperatures. So you're out of helium-4 cryogenics and into helium-3 cryogenics. Let me now show you how you can implement these SNSPDs in a physical chemistry experiment. And you have to overcome some challenges, right? There's some new challenges that have come up because of this technology. The first one that honestly scared us a great deal when we first contemplated this is that we really have to work with cryogenics below 1 Kelvin now, because the superconductivity transition temperature for this material is around 1 Kelvin. And actually, the colder they get, the better they work. So we had to learn how to run these devices And we typically now, we get daily temperatures of about 0.3 Kelvin. And I'll try to convince you this is really not such a big problem. Also, the advantage is the disadvantage. So there's no fundamental cutoff frequency, but it also means that you have extreme sensitivity to black body radiation. This naturally means that it's very favorable to use these kind of detectors with samples that like to be cold. So actually, I think your field probably is quite well set up to use these kind of detectors. Okay, let me tell you a little bit about how we overcome these challenges. Cryogenic cooling to 0.25 Kelvin is the coldest we ever had this detector. And you would think, oh, you know, everybody worries, well, you have to use helium-4, helium-3, but actually it's not such a big deal. All you really have to do is to call this company in Montana, Chase Research Cryogenics Limited, and you can buy a closed cycle refrigerator, which is admittedly more expensive than your conventional Sumitomo 4K closed cycle refrigerator, but it's not that much more expensive. And so for a little bit more money, you can actually go from an experiment running at, say, 4 Kelvin to an experiment running at, you know, 0.2, 0.3, or 0.2, 0.4 Kelvin. And this just shows sort of what you get when you order something from Chase Research. You get this box down here, this helium-4, helium-3 closed cycle system that has 2 standard liters of helium-3 charged in it. And that cost us, of course, 2,000 euros because helium-3 is ridiculously expensive. But the helium-3 that we had charged in that detector nearly 10 years ago is the same helium-3 we're using today. So we've never had to recharge it. So you have to have your shop build this radiation shield, and then you attach this helium-4, helium-3 closed cycle refrigerator to your Sumitomo cold head. And, you know, we can send you all the drawings if you want to do this. It's really just not that big a deal. And it all goes in a vacuum can with a small turbo pump to pump it out. And, you know, sort of the additional cost beyond your Sumitomo is something on the order of 30,000 euros. So it's really very doable. And we'd be happy to help you do it if you're interested in getting into this. Okay, black body radiation is another story. We want to do fluorescence spectroscopy, so we want to have a monochromator to disperse our fluorescence. If you do a simple calculation about black body radiation, you'll see a monochromator has gratings and mirrors inside. If you even, and of course the mirrors, there's direct sight to the detector of this first mirror. You can calculate the black body radiation even from a high reflectivity room temperature gold mirror is way too high. This detector will just be swamped by the black body radiation. So we first came up with a simple design we took apart a commercial monochromator and put it back together with special oils and so forth so that we could cool it down to liquid nitrogen temperature. And we used that for a couple of years, and that works quite well. And I'll show you a better design in our second generation machine in a few minutes. So a homemade liquid nitrogen cooled monochromator turned out to be essential for our first experiments. We also use some fiber optics for the mid-infrared to direct the light from point A to point B. You know, these are kind of painful. There are only certain materials that you can use. Arsenic sulfide is one of the best materials you can use, which has 99% transmission out to about 6 microns. These are typically about 100 micron core diameter. And of course, these things radiate in the infrared as well, so you need to put these in liquid nitrogen. You need to cool those to liquid nitrogen in your system as well, so you got to do some careful design to you know, get the light that's coming out of the monochromator port over here into, you know, your machine, into your detector machine. And the worst thing about these things is that they're quite brittle. So the most common failure mode is just by heating up and cooling down this spectrometer, you find that the fiber optic has cracked and you need to replace it. So that's actually best way to do it is to put this together with no fiber optics whatsoever. In our second generation, we have much fewer fiber optics. The other bigger problem with this particular set of experiments I'm going to show you now is that the core diameter is 100 microns in size, and the first SNSPD detectors we were getting are only 10 microns in size. So all the data that I'm going to show you in the next 10 minutes or so, you have to imagine we're throwing away 99% of the infrared photons that are available that are coming out of the monochromator, and so it limits to some degree what kind of experiments that we can do. Here's what the overall system looks like. We have a liquid helium cooled sample. So we have a sodium chloride surface here, sodium chloride crystal here that's cleaved with a in situ razor blade to make a good surface. We excite it with a 5 micron laser produced by difference frequency generation from a YAG pump dye laser system, lithium iodate crystal. The laser-induced fluorescence is collected on a mirror into the monochromator. The dispersed fluorescence comes out into a fiber and then into our low temperature cryostat where we have the SNSPD detector. And we count single pulses coming in here with a multi-channel scaler so that we can get time-resolved laser-induced fluorescence data. What's not shown here, but we also have is a Fourier transform infrared spectrometer just to do survey spectra so we can understand something about our detector, the sample that we prepared. So I want to show you now what happens when you try to do a laser-induced fluorescence experiment on a crystalline sample of a thick CO layer on top of a sodium chloride crystal. And the first thing I want to show you is what the FTIR spectrum of such a sample looks like. It's again showing the beauty of infrared spectroscopy. This is about 100 or 200 monolayers of CO on top of a sodium chloride crystal. And you can easily see the CO that's at the sodium chloride crystal absorbs here. And then the overlayer, the thick overlayer, absorbs as a doublet over here. And these are miles apart in the infrared spectrum, and it's trivial now to tune the laser either to the monolayer excitation or to the multi-layer excitation. What I'll show you next is what happens when you tune the laser to the overlayer excitation. Well, this is what happens. You detect the following infrared emission spectrum. You see infrared emission everywhere, and this is a result of vibrational energy pooling where you excite a large fraction of the molecules in the sample are excited to V equal 1 initially by the laser, or actually in this case they're excited to V equals 2 initially in the laser, and then through V to V energy transfer, vibration to vibration energy transfer by dipole-dipole coupling, you collect the quanta into a few molecules, and you produce molecules in a wide variety of vibrational states, and they all then emit. And here's the infrared fundamental emission region where you can see molecules in vibrational states up to about 25, 26. Here's actually our cutoff of our fiber is at about 7 microns. That's what you see the signal disappearing here. When you detect the signal in the first overtone, you can see vibrational states even going out to quite a bit higher vibrational excitation, and they drop off here because really the emission is disappearing. And you can even see the second overtone fluorescence and even up to V equals 29 or V equals 30. And so this just shows you kind of the performance of this spectrometer and the performance of the detector. It's really working over a wide range of the mid-infrared, and I think if you designed a fiber-free system, you'd go far beyond 7 microns with this detector as well. The beauty of this detector is it has the capability to do the same experiment on the monolayer, which is a simpler system than the crystal, and we can actually understand how it works. The monolayer structure is shown here. It's actually a 2x1 structure, which just means that it's tilted, has tilted odd and even rows to maximize the quadrupole interactions between the CO molecules in neighboring rows. And when you excite this with a laser, you get a large fraction of these up to V=1, and you get this vibrational energy pooling happening. And what's rather strange is not just that you get the vibrational energy pooling, but you also see there's kind of bumps in the spectrum. And we've named these base camps, which I'll think will become clear why we call them base camps. You can imagine climbing Mount Everest, and you do this in steps through base camps. That's kind of the image we're trying to create and in your mind. And I'm gonna show you then how this pooling works. Okay, so why do you get these base camps, and what does it mean to have base camps? Okay, so let's just first think about the basics of this. If you have laser excitation of CO, you first get a large fraction of the molecules into V=1. And then it's very easy to imagine that you have V to V energy transfer, and processes like this where two molecules that are in V=1 exchange energy so that one is now pumped to V=2 and the other one drops down to V=0. Because this is an anharmonic oscillator, this is exoergic by about 24 wave numbers. And because the temperature of the system is about 7 Kelvin, KT is 5 wave numbers. So there's basically no way for this process to go backwards, right? This excess energy is taken up by the phonons of the sodium chloride surface. And there's just not 24 wave numbers of energy in the phonons of the sodium chloride to give it back to make the reverse process take place. So this can basically only happen in one direction due to the kinetics. Now it's possible that two quanta can combine, 2 + 1 can go to a 3 + 0. This is then even more exoergic, so it's even less likely to go backwards. And you can have 3 + 1 goes to 4 + 0, and until you get up to 72 wave numbers, and the exoergicity just keeps increasing, and this excess energy is being taken up by a phonon in the solid. And you can quickly see that by the time you get to maybe V=8 or 9, this energy release is actually more than the highest energy phonon in the sodium chloride surface. And so you would expect, you hit a ceiling and this stops happening. And if you look at, the observations, it looks like, well, there's some kind of an optimal production of vibrational excitation around maybe V=7, 8, 9. So maybe this has something to do with the ceiling, but obviously you're able to go up much higher. And so the question becomes, how does the system do that? Is that multi-quantum, multi-phonon acceptance, or what's going on? And to explain this, I made a very simple animation, which I think makes it very clear how this takes place. Let me just get a sip of my coffee here. So what you see here is is kind of a cartoon picture of a bunch of CO molecules on a sodium chloride lattice, kind of looking down from the top. And every sodium atom is 3.98 angstroms away from its nearest neighbor. And these molecules these CO molecules all start out in V=0. And then we can excite them with a laser. And just for simplicity, I'm going to imagine that we excite them all up to V=1. And they're radiating dipoles, right? These are dipolar molecules, and there's dipole radiation now coherently in all directions, and they couple to one another. And now what I want to do is just kind of modify this picture a little bit, and I'm going to represent these vibrational quanta as little gold bricks. And I'm going to show you what kind of processes can take place, okay? And I already showed you what's possible. Two molecules in V=1 can go to 2 + 0. And what does this look like? This means one quantum of vibration moves from one molecule to another and leaves an empty space behind. That's a V=0 molecule. You can also have then, the 2 + 1 goes to 3 + 0. So you will have a quantum of vibration move from a neighbor to this molecule that's collecting. And again, this is happening because it's exoergic. It's driven, the excess energy is accepted by the crystal and doesn't come back. You can now have, the next step happens. So you get 4 quanta. You can get now even 5 quanta. And then you might imagine, well, what if I run out of neighbors? Maybe that's a problem. But you can actually, these quanta in V equal 1 are highly mobile because you have the perfectly resonant process of a 1 plus a 0 goes to a 0 plus a 1. So you can have energy migration or diffusion around the surface. And so this leads to actually availability for these V equals 1 molecules to pump energy into the energy collecting molecule until you hit this ceiling where the sodium chloride can no longer accept the excess energy efficiently, and you end up then with something like 8 or 9 quanta in a single molecule and a bunch of empty spaces around. And all these quanta around here, they will pool somewhere else, right? Because it's easier for them to pool somewhere else than to try to beat their way through the ceiling. And so you eventually then end up with a situation that looks like this, where you have a small number of molecules, all with on the order of 9 quanta vibration, but now they're on average quite, a larger distance away from one another. And the vibrational dynamics that are now possible happen on a longer time scale, simply because the dipole-dipole coupling between these oscillating dipoles is taking place over a longer distance, right? This is like a distance cubed dependence. So the second base camp now this is what we call the first base camp, and the second base camp will form more slowly due to vibrational dynamics that look like this, where you have like a 9 plus a 9 goes to an 8 plus a 10, which again is a very small energy defect, and so the sodium chloride can accept this excess energy with no problem. And here you can have, again, a 9 plus a 10 goes to an 8 plus 11, a 9 plus an 11 goes to an 8 plus a 12, and so on and so forth, until eventually, you have on the order of 15 quanta in the second base camp. And you again, at some point, these numbers become too large. Not the exoergicity of 9 plus 14, you go to 8 plus 15 is again relatively large. Eventually, you again hit this the single phonon ceiling again, and it stops, or it slows down. It doesn't really stop. So from the second base camp, which now looks like this, you can begin to form the third base camp, and this produces states up to something like V equals 20 or so. And again, it's happening even more slowly because the average distance between these interacting vibrational islands is even further than before. We've modeled this using kinetic Monte Carlo simulations, and you can actually put in the rates for these dipole-dipole coupled V2V energy transfer. See, it's quite easy to model. And if you, in your kinetic Monte Carlo, do simple things like say, here's my pooling molecule in the center, and I only let the nearest neighbors pool to it, then I actually get this first base camp, so to speak. But when I let pooling happen over a much wider range, up to the 8th nearest neighbors, which is molecules interacting over about 1,000 square angstroms or 30 angstroms distance from one another, then you can see that I am able to model all 3 base camps. And so we believe this kinetic Monte Carlo simulation is quite accurate, and I can show you now some of the results that come out of it. One of the nice results that comes out of the kinetic Monte Carlo simulation is we can see how it depends on what we assume about the phonon structure of the solid. So the simplest picture for the phonons of a solid is to simply use the Debye model invented by Debye, and it just has vibrational states or phonon states that increase their density of states until you have a Debye cutoff frequency. So we tried some simulations using this kind of sort of very unrealistic phonon density of states, and here's the simulated infrared emission spectrum that you get. then we were fortunate enough to be able to collaborate with Jörg Meyer at the University of Leiden, one of your colleagues actually, who used density functional theory to calculate the density of states of sodium chloride and calculate the projection of those density of states on the sodium atom motion where the CO molecules are bound to. And he was able to show us that not all phonons are created equal. And in fact, the best agreement with the experiment comes when you only include the transverse phonons of the sodium chloride surface, which basically means the sodium chloride surface that moves parallel to the surface itself, which is changing the distance between the CO molecules and changing the dipole-dipole coupling between the CO molecules. And you can actually construct a very simple symmetry argument, which tells you it's in fact these motions of the system which lead to non-zero matrix elements in the V2V coupling. And so this is what we now believe is the most important dynamics of the pooling, is that the transverse phonons of the solid accept the energy and lead to the pooling, and this base camp mechanism is operative. So this base camp picture basically says that the vibrational dynamics take place over a hierarchy of timescales, and the kinetic Monte Carlo tells us that base camp 1 forms in a few nanoseconds, almost instantaneously. Base camp 2 happens, is formed over about 10 microseconds, and base camp 3 is formed over about 100 microseconds. And so we've looked at then even the time-resolved fluorescence spectroscopy. You can see here in the lots and lots of data in the upper right-hand corner of each frame is the vibrational state that we're detecting through the infrared fluorescence. And these low V states are in base camp 1. You can see they appear almost instantaneously. And by the time you get up to about V equals 13, you can see now there's a lag time. Notice this is a logarithmic time axis. So this is already going from, nanosecond appearance times to about, 1 to 10 microseconds appearance times here. And then by the time you get up to say V equals 20 or so, you're seeing now another feature that's appearing on the 100 microsecond time scale. And this is now the third base camp. Okay, I've told you about the pooling process. This all happens in about, it's all over within about 100 microseconds. And then we can ask the question, what is the decay? What is the vibrational relaxation of these highly excited states look like? It's a topic I've been interested in studying for a big chunk of my scientific career. And what I'm showing in this panel is the effective decay or the observed fluorescence of these different vibrational states as a function of time after the pooling. So the pooling is like a population of many states, and then what you see is the very highest states decay most rapidly. A reason for that is that 26 is fluorescing into V equals 25 and 24 and 23, and 25 is accepting fluorescence from 26 and fluorescing down. Also, there's energy being lost to the solid in competition with the radiation. And by the time you get to the lowest vibrational states, they decay the slowest because they're collecting quanta from above, and they're also, it turns out, they're coupled more weakly to the sodium chloride surface. But we can take these observations, these are our observed, inverse of our observed lifetimes essentially, and what you see is this is what those rates look like. And we can now begin to try to interpret those theoretically. And we've used 2 different theoretical models for, obviously the infrared fluorescence is not that hard to model because it's very much like the gas phase. So that's in the model of the decay processes. But it's a big question, what do we take for how the molecule gives away its vibrational energy to the solid, right? And one way it can do is to actually give 1 quantum of vibration into the sodium chloride lattice in some multi-phonon excitation process. And normally the way we would conceptualize that is we would say that this multi-atomic, polyatomic system is governed by an electronically adiabatic potential energy surface. And we would just think of this like a coupled anharmonic oscillator problem. Here's an anharmonic oscillator, and And here's an anharmonic oscillator, and it's coupled, you know, through another very soft anharmonic oscillator. And you could simply carry out the anharmonic vibrational dynamics, and you would find that there's an energy flow. If I initially excite this CO molecule to its V equals 27 state, there'll be an energy flow into the rest of the system with a certain probability and with a certain rate. And this is called the Skinner and Tully model, which was actually proposed quite many years ago, and can be used to calculate the rates and more importantly, how this depends on the degree of vibrational excitation. So this is what we use. We use a model of the relaxation for every single vibrational state. That goes into our kinetic Monte Carlo scheme, and then we compare that to our experiment. There's another possibility which relies on completely different physics, and that is, what if I forget about the interatomic potential altogether, and I imagine simply this CO molecule as an oscillating electric dipole. And the oscillating electric dipole is not in a vacuum. It's actually in the vicinity of a material which has a finite index of refraction and also has a complex index of refraction. And so the electromagnetic radiation emitted by this dipole can, because it's a complex index of refraction, be absorbed. We always think of sodium chloride as being transparent in the infrared, but it's of course not perfectly transparent in the infrared. And this is called the Chance-Prock-Silby model, and that makes different kinds of predictions about the rate constants. And so here are the predictions of these two different models. The Skinner-Tully rate constants are actually very strongly dependent on the vibrational quantum number. And that's easy to understand because a V equals 25 CO molecule is much more anharmonic than a V equals 1 or 2 CO molecule. And so the anharmonic coupling to the rest of the system, you know, is actually much bigger. Notice these are logarithmic scales, so it scales very rapidly with vibrational quantum number. This CPS model rate constants are actually very weakly dependent on the vibrational quantum number. And if you compare them to the radiative rate constants, just the fluorescence rate constants for CO and isolated in the gas phase, you can see they look almost the same, right? They're basically the CO radiative gas rate constants scaled by some number which has to do with the interaction between the CO molecule and the substrate. So we can take these two different models of the rate constants, put them in our kinetic Monte Carlo, and compare them to our experiment. And that's what we did here, and that's what I'm showing you here. And the open circles with error bars, that's the observed rate constants I showed you before. Actually, I showed you the rate constants before, now I'm showing you the lifetimes, 1 over the rate constants. And here's the Skinner-Tully model, which obviously falls off much too rapidly. The lifetimes are much too short. And the CPS model actually does quite a good job. And in fact, if you imagine that maybe the CPS model is giving way to the Skinner-Tully model for very high vibrational excited states, you might imagine that that's what that's what gives rise to this gap here. One interesting historical side note I just want to inform you of is that this CPS model is essentially the atomic scale extension of Sommerfeld's theory of ground waves. More than 100 years ago, Sommerfeld considered how is it possible to do radio communication beyond the horizon, and because you have no clear line of sight, he realized that you can set up what are called ground waves, where you have an antenna, which is an oscillating classical electric dipole, sets up radiation waves which travel through the surface of the Earth around, you know, over the horizon to the next city. And this Chance, Prock, and Silby were actually inspired by Sommerfeld's work to extend this to the atomic scale. And it's essentially what's going on with these CO molecules. And so we like to call this limiting case for vibrational relaxation. It's really the weakest kind of coupling you can have between a molecule and a solid, the Sommerfeld ground wave limit, where the interaction between the molecule and the solid is purely through an electromagnetic interaction. Okay, I'd like to now tell you about our newest spectrometer, our second generation mid-IR spectrometer, which has some significant improvements. One is that we now have our monochromator actually packed into our cryostat with the SNSPD, so it's vastly simplified and performs much better because the monochromator now operates at 40 Kelvin. It allows us to eliminate a great deal of the fiber optics that we had in the system before. We still have a short fiber that goes from the exit of the monochromator down to the SNSPD. The next generation will eliminate that fiber as well, which is clearly not necessary. And I also want to show you the newest detectors we've gotten from the group in Boulder, which I don't know if you can see this very clearly, but they're actually 4 detectors next to one another, and each one is 100 microns by 25 microns. So we can match the size of our fiber and actually work with a detector which is about 100 microns by 100 microns. Here's the previous detector that we had before, and now it's the same size as the fiber core of our arsenic sulfide fiber. And we've also set up a molecular beam dosing system, which I'll show you in a few minutes. So the first thing that we did then with this new setup was just repeat our pooling experiment on the monolayer and see how it works. And my colleagues were very astute in realizing that with the increased signal to noise, we would be able to work with higher resolution. And so they swapped out the monochromator grading to get higher resolution. And remarkably, this spectrum that or maybe not remarkably, the lines are pretty broad, but we were quite surprised to see that at higher resolution, we actually now get 2 progressions, not 1. And the question now becomes, what are these two progressions due to? What they're due to is actually the so-called right side up and upside down CO molecules. And we've analyzed this spectrum in terms of an electrostatic model. If you spend some time thinking about electrostatics, if you bring a gas phase CO molecule, which has dipole, quadrupole, and octupole, up to an array of charges, like the sodium chloride crystal, you will quickly realize, and it's actually known for quite some time, that it will be blue shifted. And so one of these, here's the gas phase numbers. If you look at our frequencies for one of these vibrational progressions, it's blue shifted by about 5 wave numbers. But the other one is red shifted by about 5 wave numbers. And this is actually what you expect if you flip the molecule upside down. The interactions kind of reverse sign, if you will, and instead of a blue shifted vibrational frequency, you now get a red shifted vibrational frequency. And it's also interesting to note that the anharmonic constant of these 2 progressions is essentially identical, which is also a sign that you're really talking about the same molecule, just operating in different electrostatic fields. So we've assigned then these 2 progressions to the previously known C-down adsorbate and the metastable O-down adsorbate, or the flipped CO molecule. And you can read more about this in this paper if you're interested. We've taken now and developed a fairly sophisticated electrostatic model for the interaction of a gas phase CO molecule with a sodium chloride surface, which relies on gas phase quantities, which are essentially the dipole moments, quadrupole moments, and octupole moments of the different vibrational states, which are actually pretty well characterized up to quite high vibrational states. And if you do that, you can begin to understand what's going on. What's shown here is the V = 0 vibrationally adiabatic potential energy surface as a function of orientation of the molecule at a fixed distance. And you find that the energy minimum is for C down above a sodium, because of course CO is C minus O plus in its ground vibrational state. But you also see that there's a metastable state up here where the O interacts with the sodium. It's higher in energy, and there's a barrier actually to get from one to the other. And I want you to notice this number. The barrier to get from one to the other is about 500 wave numbers. I'm going to come back to that a little bit later. We also are including in this model CO-CO interactions through dispersion forces. And that's what gives rise to these slight tilting of the molecule, both in the azimuthal coordinate and in the polar coordinate. And actually the quite large tilt angle difference for the metastable. So the C down molecule is nearly vertically oriented. The O down molecule is actually tilted to quite a large angle. So to make a rather complex picture very oversimplified, you can imagine that you have in the V equals 0 state a molecule with C minus, O plus, and I go to a highly vibrationally excited state, which is O minus, C plus, and it wants to flip around. Of course, this is, it's more complicated than just the dipole. You have to consider the quadrupole and octupole moments as well, but it more or less works like this. In the monolayer, there seems to be very rapid reconversion of the O down species back to the C down. So even though we see it in the millisecond time scale of infrared emission, it's rapidly converting back to the C down. We can never isolate the O down species and, for example, take its infrared spectrum. Recently, there's been a first principles calculation done using density functional theory, using functionals that are thought to be very good at describing dispersion forces and electrostatic forces. And Wodtke recently published this paper in JPC where he showed, again, the vibrationally adiabatic potential curves that for, V equals 0, here's the C down structure, and here's the metastable O down structure. And by the time you get to very high vibrational states, you see that the ordering switches, and so for V equals 30, the O down is even more stable than the C down. So this all kind of gives you the feeling that it makes sense that you should see this upside down CO molecule in these sorts of experiments. Let me now show you what we've done with our molecular beam setup, which allows us to do some additionally kind of interesting experiments. And we've added a dosing system to our surface where we're able to simply dose for, say, a certain number of molecular beam pulses to make a monolayer of one isotope of CO. And with another molecular beam source, then we dose for, say, 100 times longer or larger number of pulses, and we can make an overlayer with an isotopically pure prepared overlayer on top. And now we can make sandwich systems. And I'm showing here now the FTIR spectra of a couple of those sandwich systems that we've looked into. This one in the upper spectrum is the heavy isotope C13018 into monolayer with the overlayer of about 100 monolayers on top of the light isotope, which from now on I'm simply going to call the 38 monolayer, 26 overlayer system. And when you take the infrared spectrum of that, you can again see how powerful infrared spectroscopy is. Here's the monolayer of the 38 monolayer absorption over here, very, very narrow. And here's the 26 overlayer absorption over here, about 100 times larger integrated absorption. You can easily now use a laser to selectively excite the overlayer, selectively excite the monolayer. And of course, you can reverse just reverse the ordering of the pulse molecular beams, and now you make a monolayer 26, overlayer 38, and the spectrum's completely different. Now you can see, here you excite the monolayer, and here you can excite the overlayer. And this gives us an opportunity to explore energy transfer between these layers and understand a little bit how that works. The first thing we did actually with this setup was we made buried monolayers, and we were able to produce the CO in the monolayer. Here's this monolayer absorption, and then we just pumped the system for a long time and retook the Fourier transform spectrum, and now we see not only the C down absorption feature in the FTIR, but we see a new absorption feature in the FTIR, which is exactly where the electrostatic model predicts the O down absorption feature should be. And when we warm it up to about 20 Kelvin, we can actually thermally anneal it away back down to the C down. So this is now showing that this upside down CO molecule lives a long time when it's in a buried monolayer, whereas in a monolayer, it does not live for a very long time. Okay, on to these phonon energy transport experiments. We can now use our molecular beam setup to make all kinds of different samples. So we can, have homogeneous samples and study the problem. Can we say put the energy at the monolayer and design a system where the energy always moves away from the monolayer? So what we might do then is to, pump the molecule in the monolayer at one frequency and then look for infrared emission that corresponds to this isotope in the overlayer. Or we might do something like this, where we pump the molecule with the 38 monolayer and look for fluorescence in the 26 overlayer. To make a long story short here, or to maybe just say what some of you have probably already figured out, is that the energy always likes to move from the light isotope in the direction of the heavy isotope. So this example turns out to be quite interesting because it's the example where you can extract the energy from the monolayer very efficiently. We can do a different kind of experiment where we ask the question, are we able to confine the vibrational energy at the interface? Can we now pump the molecule into the monolayer and do something so that it can't get out? And it turns out that this system is one where we're able to show that. And then we can also ask the question about light harvesting. Can we create a thick overlayer capable of absorbing many, many, many infrared photons and then condense, in a way, these vibrational quanta into the monolayer and more efficiently put vibrational energy into the monolayer than if we pumped it directly with the infrared laser. And so these three systems are the ones that I want to concentrate on and show you data that we've taken. So here's the first example of preparing vibrational energy in the monolayer and directing the transport of energy away from the monolayer. And you can quickly see that this isotopic combination works very well from that, because when I pump the 26 monolayer, I see infrared emission at all of these frequencies indicated by the black arrows. If I pump the overlayer directly, I get different intensity pattern because I'm absorbing a different number of infrared quanta, but I get exactly the same frequencies. And so this is just telling me right away that even when I pump the monolayer, I get rapid energy transport into the overlayer, and emission only comes out of the overlayer. I can then ask the question, can I confine the vibrational energy in the monolayer? And here I reverse the isotopic structure of the sandwich layered system, and I compare an experiment where I pump the 38 CO at the monolayer and look at its infrared emission spectrum, and I get always these blue lines, which you won't now not be too surprised. Those are the O down CO molecules, which are fluorescing. And if I now pump the overlayer, what I see is that I get completely different frequencies, and these are the 26 isotope fluorescing out of the overlayer, and I don't see those in this experiment, which tells me I've succeeded in keeping the vibrational energy in the monolayer. Finally, I can show you the light harvesting experiment, and again, now we put the light isotope in the overlayer and the heavy isotope in the monolayer, and now we can excite this overlayer, which fluoresces like crazy. That's why you see these very strong off-scale fluorescence features, but in between them you see additional features which correspond to vibrationally or infrared emission from the monolayer, and actually you find two different frequencies corresponding to the red, which is the O down molecule, and the blue, which is the C down molecule. And if you compare these now against one another, while these intensities are arbitrary units, they can be compared to one another on a relative scale. So if I pump the monolayer directly, I can induce the flipping reaction and produce the CO upside down on the surface, and that corresponds to these large peaks labeled by the red comb here, which have a magnitude in arbitrary units of 0.8. But the upside down CO molecule fluorescing in the light harvesting system is more than 50 times stronger, and you can actually see that it produces much higher vibrational excitation. So these are all signs that you've gotten many more vibrational quanta into the monolayer. And by analyzing this in a more rigorous way, you can actually come up with a good number that you're actually getting about 30 times more efficient pumping of vibrational energy into the monolayer by using this light harvesting concept than if you pump them directly. Okay, the last thing that I want to show you is some lifetime measurements, because I showed you that this upside down CO molecule could be even measured in the Fourier transform infrared spectrometer, but that was in a 7K sample. So what we've done recently is to install a so-called rapid scan FTIR mode, where we can rapidly take FTIR spectra and then use this light harvesting concept to prepare the upside down CO molecule, and then adjust the temperature to a range where we can begin to see the decay of the metastable upside down molecule into the ground state C down species. And these are quite new measurements done by Arnab Chowdhury and Jesselyn Devine. And again, you see these FTIR spectra for the C down species and the O down species, is the blue shifted C down species and the red shifted O down species. And as they decay away in time, you can measure the absorption from the O down species disappearing. And what you see is that at 20 Kelvin, it takes about 3 hours, 1/E time, for this to disappear. So these are quite long, about 1,000 minutes. So that's many hours of measurement by Arnab. And if you just raise the temperature by about less than 3 degrees, you see the rate increases by more than close to a factor of 100. So here's a 3-minute decay happening at only 22.75 Kelvin. So it's a first order. It seems to be a first order decay that varies within a factor, 2 orders of magnitude over only 3 Ks. And we can do an Arrhenius analysis of this, obviously measuring over a very dense temperature grid, and you get out actually quite precise activation energies and Arrhenius prefactors. And I want to show you and remind you, I told you that you should remember 500 wave numbers as the energy gap or the energy barrier predicted by our electrostatic model to go back to the ground state. This is actually quite close to the activation energy that we're measuring in this experiment. Well, that brings me pretty much to the end of my talk. I'll just summarize the points that I want to highlight. SNSPDs, I think most important one for you is that SNSPDs now make infrared emission spectroscopy extremely attractive for molecular science, and particularly molecular science that likes to happen at low temperatures. We've applied this to study the vibrational energy pooling in a CO monolayer and revealed a base camp mechanism. We've looked at the relaxation of vibrationally excited CO and sodium chloride and seen that it follows something called what we call the Sommerfeld ground wave limit, where electrodynamic interactions are the only thing that matters, and the interaction potential actually doesn't seem to matter at all. The spectroscopy shows us that there are clearly 2 isomers of CO on sodium chloride, a C down and an O down. The O down lifetime has now been measured for the buried monolayer, and we like to measure it now for other, burying it under different monolayers and also measure it for the unburied monolayer. We've shown how you can use these layered systems with diatomic molecules of different frequencies to control the transport of vibrational energy in the condensed phase, and even use this for an infrared light harvesting system. And that this can, a lot of this can be understood already through simple vibrationally adiabatic electrostatic model. I want to dedicate this talk to George Ewing, who was the first to discover the vibrational energy pooling in the CO sodium chloride system, and did a lot of beautiful work on this and many other problems, and is simply one of my favorite physical chemists of all time. And Also, I'd like to acknowledge and thank the group of excellent young people I have the privilege to work with here in Göttingen, and also in particular for this work, the current SNSPD team of Dirk Schwarzer, Yasha Lau, Jesselyn Devine, and Arnab Chowdhury. And finally, I'd like to thank you for your attention and be happy to try to answer any of the questions that you might have.
Thank you for a very interesting talk, Alec. Maybe you could comment on whether you think any of these effects would also be observable for CO on water.
I really don't know. And the big question, okay, we can easily make water ice. We can easily absorb CO on top of that. We can easily excite it. And then the question is, what's the interaction between CO and water ice? And it will clearly be different than CO. Well, I think it will be clearly different than CO on sodium chloride. How different, I'm really not sure. The phonon spectrum of water is different. The interactions between CO and water are stronger because you have weak hydrogen bonds. So I expect that the Skinner-Tully theory or a theory similar to that likely becomes more relevant. If you made me guess, I'd say we will see some pooling, but it won't go to such high V states because the energy will be lost to the surface more efficiently. I would be surprised if we cannot see any laser-induced fluorescence whatsoever. So I think that's, as a kind of analytic detector of CO on sodium chloride in a frequency and time resolved experiment, I think it probably will work.
We have further questions for Alec?
Yeah, I would have a few technical questions and also one question about a possible application. Perhaps you already have experience with it. First question is, you showed a number of these beautiful spectra. How long does it typically take to record such a spectrum? So in the emission?
It takes a while. It takes about 20 to 30 minutes because we're working with a simple scanning monochrometer.
Okay, and you just have to tune through, yeah. So is that somehow related to, because you said in the new spectrometer you use, you have the lower temperature, so you have a higher resolution, but that I didn't understand. So what is the temperature doing with the resolution?
Oh, the resolution is improved simply because we replaced with a new grating.
Oh, okay.
Because we had higher signal to noise, we could go to a better grating, get higher resolution. Ultimately, I think what one really wants to do is to build an interferometer and replace the monochrometer with an interferometer.
Yeah.
That, I think we've got the other aspects of the spectrometer under control to the degree where we might take on that kind of challenge. But I think this is actually now the interesting question is to make now the next generation should simply take as its highest priority getting rid of the things that break the most often and making it something that's very reliable, even if you don't really change much in terms of performance. I think a scanning monochrometer is very reliable, and so I wouldn't change that as my first goal. But again, it depends what really the application is that you want to have, and if it's essential to have, say, an interferometer for the application, then that would be a good step to take. But of course, there's going to be growing pains for that.
Yeah. And I also understand. So to get this work, I suppose there was quite a tough fight against black body radiation. Yeah, to be sure that everything is as cold as possible, that you don't catch any other signals. So I was wondering, what is the highest temperature you still can use on your substrate before you start running into trouble with your detection?
We we actually don't have that big a problem with black body radiation because we're working typically at wavelengths, longer than shorter than 6 microns.
Okay.
And so it's still not that big a deal at liquid nitrogen temperature.
Oh, okay, that's definitely. Now, the reason I'm asking that in typical work we use is typically around 10 to 20 K on the substrate. That
Yeah,
is
this should be no problem whatsoever.
No problem at all. Yeah.
And then it's going to be interesting just when you get rid of the fiber and you start looking for signals at 10 microns and 15 microns and 20 microns, when that starts to become an issue. But I want to point one thing out. Black body radiation might be your experiment because, of course, infrared emission spectra are not black body. They reflect exactly the absorption spectrum, right? So if you have a molecular sample on a cold surface that has a resonance at 10 microns, you will see that in the black body emission spectrum without a laser.
Yeah.
And that might be exactly what you want to see. You might be wanting to detect a molecule which has a characteristic vibration at 10 microns. So you shouldn't think of black body radiation as necessarily your enemy. It's something you're very sensitive to, and it could be your background. It could also be your signal.
Yeah, because that was actually also the question I had for the outlook. So we are particularly interested in dynamics and chemistry, and these ICEs taking place. Is that something that you think is doable with such sensitivity? So now you're excited with a laser, but forget about the laser, and you look for chemical reactions taking place on the surface. You have excess energy that may irradiate. Is that something that people are thinking on using these methods to monitor dynamics on the surfaces?
I know Liv is thinking about it. Since she and I have discussed this, so I've been thinking about it too. I mean, clearly exothermic reactions have a propensity to make vibrationally excited molecules, which will relax radiatively and non-radiatively. And then it's just the question, what's the competition between the radiative decay and the non-radiative decay? And if it's phonon dominated, these detectors are sensitive enough that you could very well be in a position that you would see a significant quantum yield for fluorescence.
Yeah, great. Yeah. All right. Hey, thank you very much for a beautiful talk. Yeah, thank you very much.
So I see there's a chat in my chat here. What is the typical deposition condition to grow a crystalline structure of CO and sodium chloride at extremely low temperatures in this study? Yeah, so how do we do the sample preparation? We do it in different ways. When we make the monolayer, we actually just dose it, we kind of overdose it, but we overdose it at about 20 Kelvin, where the overlayers evaporate and the monolayer anneals to the ground state structure. And then we turn off the dosing and cool down to 7 Kelvin. When we put the overlayer on, we dose at low temperature because we don't want mixing between the overlayer and the monolayer. And this makes some kind of strange, not necessarily perfectly crystalline structure and not necessarily layer by layer growth. So we've done some very recent measurements looking at the thickness dependence of this light harvesting business. And what we found, for example, is if we dose an equivalent amount of overlayer, let's say should be like 10 monolayers on top of the monolayer, we still have we still have exposed monolayer underneath. So some kind of droplet formation that you need to dose longer than 10 monolayers before you really start to cover everything. So when I say we make 100 monolayer overlayer, you shouldn't think of it some kind of flat surface that's exposed. It's some kind of funny, ice. And the reason for that, of course, is you dose at 7 Kelvin, the molecules hit the surface and they kind of freeze out. They can't diffuse very well. They can't anneal to their lowest energy configuration. And so it's actually kind of an interesting phenomenon. You can actually use that to advantage in some experiments as well. And that's an interesting question.
Do we have any other questions? If you have a question, then just speak up. No?
So I have a question for anyone in the group who might like to answer it. How do you use infrared spectroscopy in your research?
Pass that on to Harold.
Yeah, well, it's mainly direct absorption. So we use rares as a typical surface technique. So it's reflection, infrared spectroscopy, and ices with us are typically much thicker, 50 to 100 monolayers. If you want to do the real spectroscopy on the ice, it's even thousands of monolayers. And that's normally combined with complementary techniques like temperature programmed absorption. So in that combination of doing spectroscopy, mass spectrometry, eventually using isotopes normally gives quite a good tool to see what's going on in the ices. So generally, sensitivity is not the issue there, yeah. But it may be very interesting to see if you have additional tools to get information that you normally cannot reach, yeah, with rares and TPD, because quite often you have to do a lot of control experiments to be sure that your conclusions are right, yeah. And in this respect, I think emission may be very interesting. I'm also actually thinking how processes you mentioned in your talk could play a role in interstellar space. Yeah, there of course the pumping speed is much lower, so probably relaxation will have one before you can get an additional step. Yeah, but people are thinking in this direction. Yeah, so it's definitely very interesting.
Yeah, Liv got us interested in a very interesting problem. And we're going to be working with her to try something in this direction very soon, and that is to deposit some PAHs onto the sodium chloride surface and onto some ice surfaces, and then pump them with ultraviolet light, and see what kind of infrared emission can be detected. So I think that's something she made me aware of that I think really does have some potential relevance to interstellar processes.
Yeah, definitely.
What would also be to actually be able to follow the vibrational, the decay of the vibrational excitation.
That will be then on the solid, yeah. The pH is on the solid, yeah.
That's right.
It's interesting, yeah. Yeah, because you have these unidentified infrared emission bands in space that typically link to the gas phase, but obviously if you can see them in the solid state, it will be the same processes hindered by the surface, but that's it. It definitely would give you good information, and perhaps it even gives you more information on the ions being formed, because pHs are relatively easy to ionize, and you have these two processes and they can start emitting as well. That may be really interesting. Yeah.
Yeah, I hadn't thought about the ions before. That's very interesting as well. Yeah.
Right.
I also have a question.
Yes, please.
Yeah. So have you ever thought to study phonon modes directly in the terahertz range with the free electron laser?
I know people are doing stuff like this, but I haven't ever really, honestly, I haven't ever really seriously thought about it. Do you have something specific in mind that you were?
Well, because all the, well, CO, for instance, as a terahertz mode, should have a terahertz mode around 1.4 terahertz or something like that. So in that way, you would excite the phonon modes of the CO molecules directly. And I don't know if you can study fluorescence, but maybe applying a different technique there.
Are you thinking of using this SNSPD to detect terahertz? Is that what you're saying?
I don't know.
I think that's a very interesting idea. I mean, this is still an open question. How far can you go? How low energy photon can you actually detect? And if you can use it as a terahertz. Do you have a feeling how good are current terahertz light detectors? I suspect they're terrible, but I really don't know.
Yeah, I don't know exactly, because then I guess people use bolometers or radiometers at those ranges. So yeah, but there are several detectors there, super heterodyne detectors and different.
All the more reason to put together a fiber-free detector to try to look at longer and longer wavelengths.
Yeah. That would be very interesting. And then you can use a free electron laser to switch from the mid-infrared to the terahertz as well.
Yeah. There's a nice one in Nijmegen, isn't it?
Yeah, there's one that in Nijmegen. Yeah, definitely.
Yeah. Thank you.
Welcome.
So do we have any further questions? If not, then let me thank all of you and especially Alec for being present here today at our first InterCat seminar.